Very good evening, everybody. Welcome back. Welcome back to another interesting session. So today's topic for the interview preparedness is about linear regression. And we'll be discussing about that. So before I proceed further, you must be aware about the fact, you must be already aware that when we talk about prediction, there is predominantly two types of predictions that we do. One is the classification, other is the prediction or continuous data prediction. And whenever we have a continuous output, we call it regression. And regression can be of multiple types. We are going to be specifically discussing about the linear regression today. Now, there is a total flow path associated with the regression, and there's a total pardon me, there's a total prerequisites and all those things that are there. So what we'll do is we'll spend some time discussing back and forth about that. All right. So today we'll try to have more of a discussion rather than an interview, me asking the question and Sharath answering. Sharath will contribute maybe you'll use this a writing pad, Sharath, maybe if you can do that, and then we'll contribute and try to see as many things that we recollect we can add to the topic of linear regression. So I think let us start with some kind of background to regression to start with. You could probably start, and I'll pitch it.
Yeah, thank you, Nitin. Good evening, everyone. Yeah, you see my voice has changed completely because of the climatic conditions. I would say my voice has now more bass in it. So let's start. And by the way, hope you all enjoy my voice. So let's start the point of a discussion where and when and how we use regression-based models. So if I have to start from the understanding of the business requirements, we always try and look at what is our target variable. If this is something that we will have to work for in our problem statement, we already know that there is a specific target, and in our historical data, we are able to gather that target data or labeled data. Then we should go for predictive modeling, right? Predictions, or we can say prediction analytics. But further, when you're trying to predict, what is the value that we are trying to predict is a question. And here, you will have two types of scenarios. One could be a non-numeric value, and the other one is a numeric value that you would want to predict. Now, based on this, you will have to choose the appropriate algorithms which gives the numeric output or non-numeric output. So what we look at is the algorithms that we have now. What all various algorithms that are available? We'll try and map it.
Yeah, I'd like to further add in the output variable Y that apart from non-numeric and numeric, we'll also have a specific category of numeric data, which will be count data. Numeric is perceived to be continuous in nature, whereas non-numeric is categorical. But there is another thing within the discrete category, which is the count data. Of course, the models that we work with for the count data is very rare. And oftentimes, when we have count data, it is, sometimes in certain cases, it is clubbed to multiple categories. They made it into multiple categories and it becomes a classification model. But the fact of the matter remains that we do also have count data, which is a separate category, a rare one, but a separate category nevertheless. Yes, Sharath.
Yeah, good point, Nitin. And to clarify that point, I'll just take a detour from my approach. So as Nitin mentioned, we will also have to look at the data as being continuous and discrete. All right. Because when you talk about numeric data can be continuous or discrete. This discrete form of numeric data is called as count data. When you talk about non-numeric, it is always discrete. There's no question of having continuous data here. Now, what I would like to bring up here is, right, this is how I generally try to map things. Always remember, when we talk about continuous data, the data can range from minus infinity to plus infinity. So that means there are infinite possible options to choose from. So your target variable can take any value from minus infinity to plus infinity. But when you talk about discrete data has a finite set of options from which you will have to choose. Fixed set of options. So that's how I generally look at it. And when you talk about fixed set of options, even if it is numeric data, you can categorize it because it is a fixed set of options, right? If you have 10 different options, you will have to choose one of those 10 options. So that means you can categorize it. All right. So that's how I generally try to correlate things here. Now, coming back to my points, my approach. So we will take the list of algorithms that are available. You probably start thinking from a prediction analytics perspective, friends. I'm not talking about descriptive analytics perspective. In prediction algorithms, you talk about KNN, you talk about naive-based, you talk about tree-based, you can talk about ensemble models in tree-based. We talk about regression, linear regression, we talk about logistic regression, we talk about multinomial, so on and so forth. How do you remember all these different models, or how do you classify them? So all I will see is, what is the algorithm returning? What does it return when you try to use it? What is the result that is coming out of that algorithm? If this algorithm is returning a numeric outcome, then that algorithms are termed as regressors. This is an easy way to remember things. But if the algorithm is giving you a non-numeric outcome, then we call this as classifier. And remember, we can use the same algorithm. For example, I will use a KNN algorithm for both regression approach, regression calculations, that is numeric output calculations, or non-numeric output calculations as well. So based on what we are trying to calculate, you classify the algorithm into regressor-based approach or classification-based approach. So KNN regressor, KNN classifier. Right? So that is something that you have to remember.
So to add
yeah, please go ahead.
here, just about every ML approach. Now there are algorithms and there are the ML models. So every ML model, all right, or every ML model that exists, almost every ML model that exists is designed to work as a regressor and as a classifier. Whether you talk about KNN, whether you talk about the tree-based models, whether you talk about ensemble, and the vice versa, the regression, the linear regression, the word regression itself, which is for the purpose of, numeric output, can be used for discrete output, right? So what is perceived as models predominantly for classification, tree-based, etc., what we have learned, can be used for regression. What is perceived as the regression model, which is the linear regression, when it is made into a logistic regression or a multinomial regression or an ordinal regression, can be used for classification as well. So, yeah.
That's correct. That's exactly was my point, friends. So hope you got the clarity. Now, one important thing you need to remember is If your output is a numeric value, that means you're trying to find out a value which is in numeric form. Then, in order to calculate this or in order to obtain this, you will be able to use your basic arithmetic operations, the basic math calculations. So you can use any of the mathematically or statistically defined equations which explain the pattern. Right? So these are called as explainable models. Or you can also say statistical based models, because they are already defined by our scientists. And in order to express these, we use a generic formula, which is called as y is equals to f of x, the base equation. But if your output variable is a non-numeric value, then in this case, I would not be able to apply any math operations directly. It's not possible. Right? We cannot apply math equations. This is where we apply the shallow machine learning techniques. Like we try and use distance-based concept. We try and use probability-based concepts, etc., etc. So statistical equations. Now, what we're trying to bring up here in these models is try and explain the pattern which is hidden in the data. Can we try and explain that pattern given the data points? Right? And the best way to do is, or the simplest way to do is, if there is a consistent pattern. When I say consistent, we need y, but we are saying that this y gets impacted by a factor. So we call this as output variable, we call this as input variable or input variables. Multiple variables can also be there. So we're trying to see if I change this input, if I alter, because that is in my control. If I give a controlled input, then what will be the outcome that I will get?
So the objective here is, friends, to take the inputs, take the outputs, and if you believe in some kind of a magic, what makes this input make this output? So it is more of an individualistic kind of an approach. So when we look at a record, all right, a record consists of an output. Let us make it simple, and a record consists of one output and one input. We can extend it to a record consists of one output and multiple inputs. For the time being, let us assume it to be a single input. Now, when we look at the continuous outputs, we are looking at each record individualistically. In the ideal scenario, we're looking at each record individualistically. And for each record, we are trying to understand what causes or what is the relationship between the input and output. So we come up with some relationship. Let us say y as a function of x. When we then move to the second equation, we take the y2 as a function of x2. Then we go to the y3 as a function of x3, so on and so forth. Now, the objective of the entire model, excuse me, is to come up with the entire regression model is to come up with something that is consistent or that is common to all the data points. All right. So individualistically, so if you want, what is common between all these things and how can we have that common factor, which is the same model? So from y1 as a function of x2, y2 as a function of, y1 as a function of x1, y2 as a function of x2, y3 as a function of x3, y4 as a function of x4, can I have y as a function of x? So that is the objective.
That's correct. That's correct. So as Nitin mentioned, we are basically trying to find out a consistent relationship. See, where you can also look at it this way. we are trying to give, or we are trying to explain the relation between X and Y using a mathematical function. That means I'll have one equation. You can basically say Y is equals to AX1 plus BX2 plus so on and so forth. Okay. This is one equation. Now, can this equation change for every record? No, right? It cannot, because it has to generalize the cause and effect relation between Y and X. Isn't it? Say, for example, if you are a smoker, if you smoke, right? It's a very common thing, right? And there are a lot of study research has also been shown that more cigarettes that you smoke, right, less your lifespan becomes. So there is a direct correlation, isn't it? Now you cannot say that for one patient or one person, the number of cigarettes that the person is smoking, let's assume 100. The lifespan of this person is getting impacted by, let's say, 20%. That means he will survive for 80 years, assume. You cannot say that another person who is smoking, let's say, 100 cigarettes, he will die early, 40 years. This is not consistent relationship, isn't it? So we are trying to explain the consistent relationship so that we can generalize the cause and effect relation between the input and output variable. That happens with a single mathematical equation. And everybody is familiar that if I have a consistent linear relationship, then it would become very easy for us to solve the problem. And that can be done using Y is equals to mx plus c equation. Right? So I'm basically saying that my data has consistent relationships here. Practically speaking, these data points are varying. They don't have consistent relationship. But nevertheless, it is very close to being consistent. And we're trying to draw a straight line through these data points, which can generalize or which can explain the overall relation between X and Y. Right?
So
And we are trying to figure out what is Y, so what is M and what is C. Yes, Nitin, please.
So to basically add on to what Sharath is already saying, friends, is in an ideal or in an ideal situation, the data points between X and Y will be such that it will be connected by a straight line. So you have data points 1, 2, 3, 4, 5 in such a way that there is a straight line that will cover the entire data points. That is the ideal situation. Now, if the data points aren't, obviously in the real life scenario, the data points aren't going to be perfectly in that particular scenario. So what is the next ideal situation? So you imagine or you try to visualize by the minimum effort, if I could, push these data points to the line. So where should I keep my line in such a way that the data points have to move a minimum amount of distance to come to that line? Is the line where we have the line of best fit. This is a way of virtualizing or visualizing how the model works. But again, this is of course the explainability or the visual appeal for this is only limited to when we have one input and one output. To a certain extent, maybe with two inputs, X1 and X2, maybe we can have, suppose some kind of a 3D plotting to understand that. But the logic behind that is only extended when we have multiple inputs. You cannot really plot it to understand it. Yes, sir.
Yes, we are also considering only two-dimensional data so that explainability becomes easy. But of course, mathematically, we just extend the same discussion for a multidimensional space. Now, in this equation, right? So as Nitin mentioned, I need to try and find out the line basically which is closest to the data points, right? So that means when you have all these data points spread in the x and y plane, what is the equation or what is the line which allows the data points to reach that line as quickly as possible? Or in other words, you can say, what is the distance of each data point from that line, right? The line which basically gives the least distance, considering all the data points, would be our best fit line. Now, in order to identify this, we need to actually calculate what is M and what is C. And that's basically what regression analysis is all about. And this best equation is identified using a concept called as OLS, which is basically nothing but variance calculation, variance in the data. And that variance is being captured by your line, ordinary least squares. When you talk about this distance, it is like your distance from the data point to the center, that is your line. So imagine this distance is your error. I'll represent that with E, because you want to predict or you want to calculate or identify this data point. Let's assume this is the data point that you want to calculate. Let me change the color. But what happens is when you use this equation and try to substitute the value of x, and when you're trying to calculate what will be the value of y, then you would get the data point on this line. So you actually wanted this point, which is called as actual value, but you would get a point on the line, which is your predicted value. So the difference that you are seeing here should be the least, right? We call that as error. E is equals to actual value minus predicted value. So as I said, this component should be least for any given line for the given data set. That means I'm not talking about one record. I'm talking about all these data points that I have. Okay. Total error should be least. And when you say least, practically the least error is 0. From a magnitude perspective, the least error is 0. So I need the total error as 0. Right? That's basically is going to be your best line. So for identifying this, we need to find out a line which is at the center of all these data points so that positive errors and negative errors are nullified and you get summation of the error as 0. Magnitude becomes.
Yeah, I'd like to interrupt here to address a question that has come.
Yes, please.
Somebody has posted a question. I'll answer that as well. So best fit line is only possible with two variables, sir. This is a question in one of the social media platforms. So if you're going to use the word line to explain the problem, no doubt, it is only possible between one input and one output variable. But the word line is generically used, or which also refers to the model. All right. So instead of using the word best fit line, if you use the word best fit model, which is a function. Now, in this particular scenario, if you notice, the function is y is equal to mx plus c, where x is the variable, m is the slope, c is the constant or the y-intercept. If you have two inputs, the same equation will become y is equal to mx plus nx, mx1 plus nx2 plus c, where m and n are the two coefficients for two inputs, x1 and x2. Now, obviously, when I try to plot this, I will not be able to do it on a two-dimensional space and explain to you how this really works. But if you visualize it on a three-dimensional space, this line is a two-dimensional plane. You imagine a piece of paper being held in a three-dimensional room, right? You're holding a two-dimensional paper. So all the points on that two-dimensional paper is your output or the Y. Now, we use the word line in a generic term. Essentially, it is a model. Now, if I go from three-dimensional to four, meaning I have three inputs, x1, x2, x3, and the output Y, we humans do not have the capability to visualize that. The matter ends there. The appearance of the model is Y is equal to beta naught. Now we change it to, enough of M N O P Q. We change it to Y is equal to beta naught, where beta naught is the, Y-intercept, which is C. Beta 1 could be M, beta 2 could be N, beta 3 could be LMNOP, so on and so forth. All right. So instead, we use beta 1, beta 2, where these are the coefficients. And it is a model and not a line. So I'm assuming your question was not with reference to specific English line. Yes, line means two, but strictly speaking, it is not between two variables. It is between one output variable and one or more input variables. That is the answer.
Yes, very well mentioned, Nathan. So there's that small difference that you people have to also identify, right? So when you're talking about regression, for understanding the concept's perspective, we will always try and understand from a two-dimensional space because it is easy for us to visually see. That gives us better understanding of the concept. But practically, you will have many variables. And always remember, you're talking about identifying these values irrespective of how many domains or how many dimensions you have. The point is you need to understand what exactly is this telling us. What does this M tell us? So when you talk about the straight line, M speaks about this slope, this part. That slope basically says that if you're changing X by 1 unit, so X is getting changed by 1 unit, then this change is impacting Y as well. That is your output variable, desired value that you are seeking. It impacts that output. So that impact is by M units. Rate of change is M units. Right? So that is the interpretation, friends. So we are trying to establish the relation between output and a variable which is causing an effect in that output. Right? So this change that we are observing is causing due to the change in X. Oops. All right. So yeah,
basically that kind of brings us to the end of today's session. We just have less than a minute left. Of course, the time is over. The regression topic is not over. It is something that we do for a lifetime. All right, people do more advances. We will in the real interview, people are going to ask you about various other scenarios, various metrics that are used to understand the quality. I think it's a pretty straightforward scenario that the objective of a regression is to minimize the error, the overall error, and it will work towards it. But there are other metrics as well to communicate about whether or not the model is good, how good the quality of the model is. Right? There are certain standards, like you have the overall p-values, the individual p-values of the coefficients. You have the R-square, adjusted and multiple R-square. You have the Jobron-Durbian values. You have the confidence interval. So those are the things which these are the things that we will have to be looking into. So yeah, like I said, each one requires a separate session altogether. But nevertheless, let's start. So we'll be doing more and more depth. We'll be doing in subsequent sessions. So please do continue to support us. Thank you so much. Have a great weekend ahead.
Thank you all.